Hi, I am Pieter Abbeel. I'm very excited to share with you some of the recent trends in artificial intelligence and robotics, and also want to say a quick thank you to the Neighbor Connect Foundation and SEF2022 to host me for this presentation. So let me start with a bit more about myself. I am a professor in AI and robotics at Berkeley, where I do teaching and research on these topics. I also am founder of a couple companies. I started a company called Gradescope several years ago. At Gradescope, we build artificial intelligence that can help grade homework, exams, projects. I started a company called Covariant. I'll talk more about that one later. But at Covariant, we built the next generation of robotic automation powered by latest and greatest artificial intelligence. I'm also a host of a podcast, the Robot Brains podcast, where I host many of the AI researchers, pioneers, entrepreneurs, let them tell their stories. Big opportunity to learn more about a lot of what's going on in the field. In the past, I was a research scientist at OpenAI, and I'm still an advisor to OpenAI, one of the big AI research institutes based in San Francisco, initially funded by Elon Musk. And as of recently, I'm also a venture capitalist. I'm one of the investment partners at AIX Ventures, where we invest into AI-oriented startups. So, 2015 is probably when AI became mainstream news. You could have seen headlines like Stephen Hawking saying AI could end mankind. Similarly, Elon Musk saying AI is the biggest risk we face as a civilization. Then, soon thereafter, Elon Musk investing $1 billion in OpenAI to start building AI. Of course, the rationale here being is that if it's built right, AI can give us so many benefits, but we got to make sure we build it right. Governments have started paying attention. Here you see a list of many countries who have put programs in place to foster the AI ecosystems in their countries. Started with Canada, no coincidence, because as you'll soon learn, the early breakthroughs of the current modern AI era happened in Canada. But from there, many other countries followed suit. A lot of money is going into AI. Look at the private or startup investments in AI. Over recent years, it's been going up very, very quickly, reaching close to $100 billion of investment in 2021. Life of a professor in AI has changed dramatically. Before 2015, I was mostly just sitting in my office, chatting with my students, giving some lectures, answering some emails, reading some books, some papers, and so forth. Since 2015, literally everybody got excited about AI. And so, for example, here, I'm at a private event hosted by Jeff Bezos, where Jeff wanted to learn more about AI and robotics. And then here's me at one of the premier conferences in our field, presenting to close to 10,000 people the latest advances we made in our lab at Berkeley. So you might wonder, with so much excitement recently, is there some hype? And yes, for sure, there is a good amount of hype. But there's also a lot of real progress being made. And so what I'd like to do here is to share with you some of the real progress being made, help you understand it, help you understand how it might apply to maybe your jobs now or in the future, and also help you understand where you can go learn more even after this session. So, what's our plan here? We'll first look at the core of modern AI, which is deep learning. Then we'll look at many applications that are powered already by deep learning. Then we'll look at modern AI and robotics, an area I'm personally very invested in, especially, of course, through the company Covariant. And at the end, I'll give you a few highlights of how you can go learn more beyond just this session here. So let's start with the core of modern AI, deep learning. Well, why is AI even hard to build? For example, why is it hard to build a computer vision system that can recognize what's in an image? Well, to us, this image is obviously some kind of dog, but to the computer, it's just a bunch of numbers corresponding to the pixel values at each location. And so the question of building an AI that understands this image It's really the question of building an AI that somehow processes these numbers and turns them into an understanding, this is a dog. People try this for many years, tried to write computer programs, if, then, else, and so forth, to try to recognize what's in images. Didn't succeed. But as of recently, we have an approach that does work. And the approach that does work is to set up large neural networks to process these images. So our brains are large neural networks. And so what this is really inspired by the brain. Even though we don't perfectly understand how the brain works, we know the brain has many neurons that make connections. And as we learn things about the world through our lives, these connections get strengthened or weakened to reflect the things we observe. And so same here with these engineered neural networks that live in computers. There's a bunch of neurons, input neurons, taking in the pixel values, passing these values on to the next layer of neurons, next layer of neurons, next layer of neurons, and each of these neurons does a tiny bit of processing. But by having many, many neurons all do a tiny bit of processing, together they do a ton of processing and might be able to reach the conclusion that this is a dog and activate the output neuron that says dog. Now, the strength of the connections between the neurons will determine what this network as a whole computes. And so the big question is, how do we wire up this network correctly such that it makes the right decisions? Well, doing this by hand is impractical, but what has been shown possible is to have the network learn the wiring it needs to have from data. So to build a computer vision system that understands what's in images, what is done today is you collect a bunch of images, for example, images of cars, images of cats, images of dogs, and then you feed those images into this large neural network. And by the way, these neural networks are much larger than the ones shown on this slide. It's just to fit it on the slide. That once actually used will have billions of neurons in them. And so you feed these images in, and so image is the input to the neural network, and then there will be output neurons, and we'll also tell the neural network which output neuron should activate for each image. And then from these examples of input image and corresponding output neuron that's supposed to activate, the neural network internalizes the pattern, starts rewiring itself, and starts doing the right thing even for images it's never seen before. Now you might wonder, how big a deal was this? How much progress did we make by going from the old school approaches to deep neural network training from data? Well, there's a competition called ImageNet. And in this competition, you get to send in your computer program that then is run over a secret stash of images, and the organizers report out the error rate of your program in telling what's in each image. You see that the best program sent in 2010 had about a 30% error rate. It's a pretty high error rate. And actually, with traditional computer vision approaches, this wasn't getting any better. But then in 2012, Jeff Hinton and his students, through deep learning, training large neural networks from a lot of data, were able to show that their network called AlexNet can drastically outperform these traditional approaches. People saw this and realized that this is actually the way to go. And since then, that's how people have been working on computer vision. And we see a drastic improvement over time. In fact, by now, the competition has been retired because human-level error rates have been achieved. Now, in the example I described, the input was an image, and the output was which neuron should activate, cat versus dog versus car, and so forth. We can do more complex things with this. You can have input be an image, and output be a whole sentence. What does that mean, a whole sentence as output? Well, English has about 200,000 words. And so what that means is that for the input image, we now tell the neural network which of the 200,000 neurons, each corresponding to one of the English words, has to activate on the output first, which one has to activate next, which one has to activate after that, until we have the complete sentence. And it turns out if you provide enough examples to your neural network, it can start internalizing the pattern of turning an image into a caption. And so, for example, bottom left here, input to the neural network is the image, output, girl in pink dress is jumping in air. This is actually really good. You can do other things. You can decide that you're going to annotate every single pixel in your image. And for example, self-driving car companies will do this because your car, if it's a self-driving car, needs to know what everything is around it. And so then the neural network will be trained with input image, output for each pixel what's there. A pedestrian, a bicyclist, maybe a car, and so forth. You actually use computer vision probably almost every day. The system for unlocking your phone takes a picture of you when you get your phone, and then in the future takes new pictures of you, and the neural network has to decide, is this person right now looking at the camera the same person as the original picture that was taken to essentially put the image encoding on the phone. Use it almost every day, works really well. Now, so far, what I've talked about is neural networks doing image processing tasks. But actually, the fundamentals are not specific to image processing. It's saying some numbers are going in and some output neurons activate according to some pattern. Well, speech recognition can be solved exactly the same way. And in fact, it was also Jeff Hinton and his students that did the major breakthrough here, the switch from traditional approaches to deep learning approaches, and now getting much, much better performance than was possible before. And in fact, you can go from language to language, in this case, Chinese to English. If you have a large enough amount of data, where you have a Chinese sentence and an English sentence, you can then train a neural network to start to understand the pattern for what input should you generate what output, and then generate translations for new sentences it's never seen before that are actually very good. What's the big picture trend here? Traditional approaches, even traditional machine learning approaches, as you fed them more and more data, at some point they stopped learning more. It wasn't helpful to feed in more data. But when you train very large neural networks, and sometimes they do have to be very large, of course, they keep absorbing the data, keep absorbing the patterns in the data, and you get better and better performance. And that's something really amazing that we've seen happen in the last 10-ish years, where more data tends to almost directly imply better performance. Of course, beyond the data, you need to compute to process the data, and you might need some AI expertise and innovation to design the neural nets the right way, to absorb the information from the data. But ultimately, the big picture trend is that with enough data, compute, and some AI expertise, neural networks can internalize the patterns in your data. So, now that we understand the core, the foundation of modern AI, which is training very large neural networks from data, data that has an input and a corresponding output, and the network internalizes the pattern, let's take a look at some other applications that we can build with this. And hopefully some of these are directly relevant to you, and maybe some others can inspire you to think about, oh, if this application is possible, maybe this other thing in my own domain is going to be possible too. So, image recognition, speech recognition, machine translation, we covered a lot already, but there's more. For example, you can do image recognition on X-ray images. In this case, a large neural network was trained to recognize whether or not a patient has pneumonia. And so, from enough X-ray scans that were annotated by doctors, then the neural network internalizes the pattern and recognizing whether or not there's a sign of pneumonia. Here's another one, very different domain, predicting wind patterns. So DeepMind, a startup out of London, since acquired by Google, they showed that neural networks can more reliably predict wind patterns that are coming up. Now, why does this matter? Well, if you run a wind farm for electricity generation, this allows you to run your wind farm far more efficiently than if you can't predict what's coming up. And in particular, you can be far more efficient in terms of what kind of backup power you need to spin up at what time, if you know when you can rely on wind and when not, more precisely. Another thing that was shown, this is a Google result, they trained neural networks to understand how long it takes to get from point A to point B. You've probably used Google Maps, Apple Maps, similar things before. Well, they give estimates. And now these estimates are much more precise than they were before, thanks to large amounts of data, training neural nets on that data. Here's a completely different example. Ocado, a grocery store in the UK, does neural net training to predict when they need to replenish all kinds of stock and can do it more precisely that way, running a much more efficient operation. Here's a completely different one. A big open problem in biology for a very long time has been the question for a protein. So a protein is a sequence of amino acids. If we know the sequence, can we know the 3D structure it'll fold into? And the reason that's interesting to know is because the 3D structure is how the protein lives in the world. And so the 3D structure will determine how it interacts with the world. And so it's very important to understand the 3D structure. But it turns out that measuring the 3D structure directly is very expensive. In comparison, sequencing a protein, knowing what the sequence of amino acids is that constitutes the protein, is very cheap. And so if we can somehow just sequence the protein and then predict the 3D structure, that would be really helpful. And so it turns out that DeepMind was able to show that a neural network can be trained from enough examples to go from sequence of amino acids to what the 3D structure will be. And what we're looking at here is in green is the X-ray crystallography 3D structure measurement, which is very expensive to do, but is done for a limited amount of proteins. And then in blue, the prediction from the neural net. And we see in both cases, and these are just examples, but it's true for many, many examples, the predictions are very precise. In fact, there's a competition around this, and what we see is that with traditional methods, which was based on essentially simulating the physics of these proteins, trying to simulate how they would fold based on first principles. Now you might say, don't we know physics? Shouldn't we get it right? If we simulate physics, shouldn't it fold the right way? And we know the result. Well, the reason that didn't work so well is because to simulate physics super precisely at the quantum physics level for molecules the size of proteins has proven too expensive for today's compute, at least. So people had to make approximations, use approximations to the true physics, and simulate with that. And when you simulate with these approximate physics models, you get some reasonable predictions, but it turns out that a neural network trained on enough data can predict more precisely. AlphaFold is that neural network, and in generation 2 of AlphaFold actually got a level of result that many people said, okay, this is it. This is now essentially a solved problem, at least for protein families where we have enough data available. Under the hood, it's a large neural network. It's actually pretty complex how it was architected, in the sense that this required some extensive biology expertise as well as neural network architecting expertise. But what they did is they take in the sequence, then go find similar sequences in a database of protein sequences. Why would you do that? Well, one thing, if there's a similar sequence that already has a 3D structure, of course, then you might end up knowing what the new one also should be. But very often, you just have sequences. You can still get information from it, because evolutionarily, if some site remains unchanged, so many sequences have that same site, it means it's probably important for the function of the protein, and probably is something that is fundamental to the structure of the protein. Whereas parts of the sequence that have changed a lot might be less critical to the structure. And so there's a lot of information that somehow the neural net starts internalizing from these other sequences and then ultimately predicts the 3D structure of the new protein that we just had the sequence for. Here's a completely different one. And you see DeepMind comes back a couple of times here because it is one of the leading AI companies in the world. DeepMind showed that a neural net can learn to play the game of Go, a very difficult game for computers to master. Before this result, there was a very big gap between the best human players and the best computer player, but they bridged the gap, in fact, got better than the best human players. At Berkeley, actually, we have done some really interesting things, at least I'm very excited about, where robots learn from their own trial and error. So they try things, and sometimes the running is more successful than other times, and then they internalize those more successful attempts as positive examples and the less successful attempt as negative examples to then reinforce, essentially, again, train the connections in the neural network to become more likely to succeed in the future. And what you see here is a robot that, from its own trial and error, learns to run. So these things are becoming possible even for physical systems like robots. And the beauty, of course, is that when you have the robot learn to run, once you have a piece of code for learning to run, you can run that same piece of code for another robot to learn to run. This is very different from a traditional engineering approach to solving these problems, where for every robot, a person would have to think through very carefully exactly what it means for a four-legged robot to run, a two-legged robot to run, and so forth. Here's something that's recently come up that's only been possible with very large neural nets that are recently becoming available, which is reliable text generation. So you provide a prompt, a sentence or two, the neural net takes that in and then predicts what are natural next sentences to generate. This can help you write articles, write emails, and so forth. Here's an example. A train carriage containing controlled nuclear materials was stolen in Cincinnati today. Its whereabouts are unknown. That's the input to the neural network. And then here's what it generates. The incident occurred on the downtown train line, which runs from Covington and Ashland stations. In an email to Ohio news outlets, the U.S. Department of Energy said it's working with the Federal Railroad Administration to find the thief. And then a quote from the U.S. Energy Secretary, and so forth. This all makes sense, and that's very interesting. How come it can complete this article in a meaningful way? Because it's read so many articles on the internet where it's been asked to learn to complete them from the beginning, complete the remainder, and at some point it internalized the pattern of how humans write articles, and it can now write an article on its own. You can do the same thing with images, actually. On the internet, there are many images with descriptions of what's in the image. So you can actually, earlier we saw you can train a neural net to go from image to text. Here we do the opposite. You input the text, out comes the image. So here's text. A masterful oil painting, a Persian exotic cat discovering their astounding crypto losses while checking their phone. Okay. We can imagine what this might look like. The neural network also, it turns out, can imagine what this might look like and can generate a piece of art matching this description. Here's another one. A Victorian man struggles with his addiction to TikTok. We can imagine what it looks like. Victorian man, Victorian era. They didn't have TikTok at the time. We can imagine what if they had TikTok and struggling with an addiction, what it could look like. Here's what the neural network generates. The man is holding a flask, struggling, holding alcohol flask, it seems, holding his phone, because that's where you access TikTok. Darth Vader realizing he's forgotten to add an attachment to the email. We've all been there. Feel stupid. Feel kind of defeated, right? Well, here's what the neural net thinks this will look like. Again, the neural network understands this text enough, and they can generate an image that reflects it. Here's the last one. A photo of a Shiba Inu dog with a backpack riding a bike. It's wearing sunglasses and a beach hat. Here it is. And so what's also interesting about these is that there are no real-world pictures of these situations. But the neural net has seen so many different pictures, has seen pictures of Shiba Inu dogs, has seen pictures of people wearing sunglasses, maybe even dogs wearing sunglasses. Probably never seen a dog on a bicycle, but seen people on a bicycle, and can somehow imagine how, based on the things it's seen in the past, what this new thing should look like. Okay, so we've looked at the core of modern AI, which is deep learning, and in essence, which is data-driven learning of patterns, allowing to essentially develop many new applications, many more, of course, than I've just shown here. Hopefully, your imagination is already thinking about some other applications beyond what we talked about here. What I haven't talked about much, except for one quick highlight, is how modern AI will affect robotics. And that's something very close to my heart. And so I'm going to tell you a bit more about that. If you look at robots right now in the world, where are they? They are in car factories, electronics factories. That's pretty much it. Why is that? Why are they not doing recycling? So much of our stuff is not getting recycled because we don't have the labor. Why are they not picking the fruits, vegetables on the fields? So many of them go to waste. Why are they not helping out in warehousing, fulfilling our orders by picking things from shelves and so forth? Why is that? It turns out that these kinds of problems are much harder than traditional car manufacturing automation. In traditional robotic automation, it's done in highly structured environments. Pre-programmed deterministic motions can get the job done. But this next generation that's just around the corner, thanks to this modern new wave of AI, deep learning powered AI, AI-powered robotic automation will be able to function in less structured environments and produce intelligent, reactive behaviors. I'm not the only one thinking that. It's actually a lot of people thinking this. Here's a little map of companies working in these spaces. Bunch of companies in recycling, farming, warehousing, automating a lot of these tedious processes that require a robot to understand what they're seeing, react to it correctly, in context, even in situations they've never seen before, items they've never seen before, still succeed. It's a very hard problem, but it's at the cusp of becoming possible. And in fact, as some of you might know, I started a company called Covariant, where we're focused on the warehouse robotic automation part of this. And we've made a lot of progress. So what you see here is a robot that's doing autonomous pick and place in a warehouse in Germany. It's just one of our many robots out there in the world now doing this. Just a few years ago, no such solution existed. But now this is becoming possible. And under the hood, it's powered by the same things we've been talking about earlier. It's powered by very large neural networks trained on large amounts of data, in this case, to learn to do reliable pick and place. So, if this all got you excited, and maybe you want to get involved more in AI going forward, let me give you a couple more pointers before we wrap up here. One thing is that maybe you're not going to build your own AI. You just want to evaluate AI offerings. Say, is this a good AI system for me to use, or should I go use this other AI system over there, and so forth? What's the right choice? With traditional products, when you buy them, you can look at the feature list. What features are in product A? What features are in product B? Compare them, and then choose based on that, and maybe based on price, what you want. With AI systems, it's actually very different. Because modern AI systems are trained from data, you need to understand specifically how well it'll work in your case. What if somebody trained, for example, this would be pretty extreme and not the smartest, but let's say they trained a face recognition system on only Asian faces in their data set. And now you want to also recognize black faces, white faces, and so forth. Well, it's not going to work because it doesn't have the right training data. But generally speaking, it's really important to understand that. And so it's not enough to just say, oh, this is a system for face recognition. This is a system for maybe product recognition, maybe for fraud detection and so forth. You need to understand that there's a close match between your situation, your data, and the data the system was trained on. If there's good alignment, it's probably a good fit. And if it's a high-quality vendor, their system will probably work well for you. If there's poor alignment, actually it's not going to work most likely, and you might need to hire the vendor as a consultant or do in-house work with your own data to get something trained up that is good for your own data. Now, if you do want to do something yourself, what's the background for building the AI systems I've been talking about? Well, undergraduate level computer science comes in very handy because ultimately you're programming things here. Undergraduate level mathematics, specifically linear algebra, optimization, statistics, those are super helpful foundations. And assuming you have those foundations, then you can start diving into the deep learning itself. And I have a couple of recommendations here, things you could check out. deeplearning.ai or fast.ai. They cover the basics, ground up. And then once you are a bit more advanced, you can, for example, check out Berkeley CS182, the deep learning course, which will give a deeper dive into the field. If you want to go learn more from many of the pioneers in the field, I have a podcast, as I mentioned at the start of this session, the Robot Brains podcast. I've hosted many of the pioneers, including Andrej Karpathy, who has led the autopilot team at Tesla, Jan LeCun, who leads AI at Facebook, I've had Keenan Weierbach, who's founder of Zipline, one of the most successful drone companies out there doing deliveries of medication and so forth. Mike Volpe, one of the partners at Index Ventures, which is actually an investor in Covariant and in many of the leading AI companies, Mike would give you a more investment perspective on the space, what makes for a good AI company to invest into, and many, many others. Ilya Sutskever, founder and director of research at OpenAI. I recommend you check this out. Available on Spotify, Apple, YouTube, and so forth. Thank you. Bye.